Assalamu alaikum everybody. I'm going to record this lecture because today we had a problem with the projector and the computer, so I'm covering chapter 25. So let's begin at the beginning of the chapter. Okay, so let's speak about capacitors. Capacitors are widely used in many circuits. They can be used in computer memories, in radio and television transmitters and receivers. They are used also in circuits that are called filters to clean the audio or video signal. And also they are used in energy storage devices. So they can be used, for example, the flashlight of your mobile or your camera is based on a capacitor storage of energy and discharge in order to generate the intense light. They usually come in different sizes and shapes. So there are cylindrical capacitors, parallel plate capacitors, and even there are variable capacitors. Okay. So really a capacitor is made up of any two conductors, two plates or two conducting surfaces. If they are connected to a battery and they are charged, they can be used to store charge or energy. So usually when we charge a capacitor, one plate has a charge plus Q, the other plate has a charge minus Q, and they are related by the equation that Q is equal C delta V. So the charge Q is equal C delta V, where delta V is the potential difference between the two plates of the capacitor. C is the capacitance and Q is the charge that is accumulated. This is the symbol that we use in electrical circuits for symbolizing a capacitor. Okay, so again, this is the governing equation. It says that the charge that can be stored on a capacitor is equal to the capacitance, and we will see what the capacitance depends on, times the potential difference across these two plates of a capacitor. Okay, so the units of capacitance are farad, and if you can see, capacitance is Q divided by delta V. The units for Q is a charge, coulomb, and the unit of delta V is volt. So farad is 1 coulomb per volt. Okay, and so the capacitance of a capacitor is the amount of charge that the capacitor can store per unit potential difference. So C is equal to Q divided by delta V. So the amount of charge that it can store per voltage difference established across its plates. So usually we connect the capacitor to a battery through a switch, and usually in circuits we don't draw this diagram. We use symbols for the different components, and so for a capacitor we use this symbol and we put C. For a battery we use this symbol, and so a negative and a positive plate of the battery. The positive plate is indicated by a longer line, and this is a switch. A switch is in open position, or it can be closed, and then we have a switch in the closed position and it will conduct current. Okay, so a battery is a device that maintains a certain potential difference between its terminals by means of internal electrochemical reaction in which the electrostatic forces can move internal charges. So some batteries are based on electrochemical reactions. Some batteries are based on other principles, but most of the batteries that we're using are electrochemical batteries. Okay, so a battery normally provides a constant voltage, but after using an alkaline battery, for example, after some time, the voltage will decrease, and that's when you need to change the battery to a new one. Okay, but the battery in general maintains a constant potential difference across its terminals. Okay, so this is a capacitance connected to a battery through an open switch. This is when we close the switch, and when we close the switch now, the electrons can flow in the circuit. So they can flow. They cannot flow through the capacitor, as we will see, because capacitor has usually the space between the plates is filled with an insulator, either air or vacuum or other dielectric material. So, but the electrons can flow in the outside circuit, as we will see later on. Okay, so let's see how we charge a capacitor. Let's assume a capacitor is connected to a battery, but the switch is open. Okay, so there is no flow of charges in the conductor or the wires of the circuit until we close the switch. Okay, so there is no excess charge on the capacitor. When we close the switch, okay, we start charging the capacitor, and the electrons actually start moving. So the electrons they will start moving towards the positive terminal of the battery and away from the negative terminal of the battery. Okay, so because the positive terminal of the battery establishes an electric field which points away from the positive charge. So if we have an electron, it will experience a force in the opposite direction because it's negatively charged. So if we have an electron, it will experience a force Fb towards the positive terminal of the battery. Okay, now since this charge is going away from the plate of the capacitor, which was originally neutral, then it leaves behind a positive charge on this capacitor plates. Okay, so again, so the electrons are moving away from the or towards the positive terminal of the battery, leaving behind a positively charged plate. On the other side, the electrons are moving in the other direction. Okay, remember the electric field points in this case towards, so this is the electric field. Okay, or this is the electric field here. Okay, so the electron will be experiencing a force in the opposite direction, so the electrons will flow towards the other side of the or the negative side of the capacitor. So we have accumulation of positive charges in this plate and accumulation of negative charges on this plate. This will continue, but remember, these positive charges here are going to generate themselves an electric field in this direction. Okay, and hence they will start again attracting the forces, attracting the electrons, the free electrons. So this will continue until the actual forces on the electrons are cancel each other. So again, this is the okay, so this is the electric field. EC is established by the positive plate of the capacitor, and it will attract the electrons to the positive plate of the capacitor. Okay, this will continue until the two forces cancel each other, and that will happen when actually the potential at the positive plate of the capacitor is equal to the potential of the positive terminal of the battery. So now, when the electric field EC and EB, they are equal to each other, the two forces cancel each other, and we have no more electrons flowing. And in that case, we say the capacitor is fully charged, so we will have an accumulation of charge of Q here and minus Q on this side. Okay, so this is charging a capacitor. So after a long time, the capacitor is fully charged. Electrons stop flowing when the electric potential on the positive plate of the capacitor and the positive terminal of the battery are equal, and the electric fields from the battery and the capacitor are equal. Okay, so once the capacitor is charged, is fully charged, okay, then we said let's say the potential difference is here delta V. Actually, when the capacitor is fully charged, the potential difference across the capacitor plates is going to be equal to delta V also, which is the voltage of the battery. Okay, and what's very interesting is when we disconnect the capacitor from the battery, this is a very nice property of the capacitors, they will maintain the charges as long as there is nothing connected. There is still a positive charge Q and charge minus Q here, so this is Q and minus Q, and also we will have a potential difference delta V. Okay, which is now the capacitor can operate like a battery for another circuit. So if we connect another circuit, for example, if we connect a resistance to this capacitor, we will have a flow of current through this resistor until the capacitor is discharged. So that's why capacitors are used as sources of energy or sources of charge in many circuits. But it's only a temporary source. Unlike the battery usually lasts for a long time. A capacitor, once it's connected, it will start discharging through the circuit connected to it. Okay, so when the battery is disconnected, the charge remains on the capacitor with a potential difference equal to that of the battery. Okay, so what is the capacitance equal to? The capacitance is actually equal to the area epsilon 0 times the area of the capacitor plate divided by the distance between the two plates. So this is the area of each of the plates of the capacitor. So this is a parallel plate capacitor. The distance is the separation between the two plates. So this distance can be filled with air, vacuum, and or another insulating material, another dielectric. And we will see when we change the dielectric from air to something else, actually the capacitance will change. Okay, so the capacitance depends on the geometry. It depends on the area. As the area increases, the capacitance increases, but it also depends on the separation between the plates. And notice, as the separation between the plates increases, the capacitor decreases. Okay, so let's prove this relationship. Let's prove this one. So let's assume we have these are the two plates of the capacitor. One has a positive charge Q and one has a negative charge minus Q. And so we have an electric field between the two plates, and remember, the electric field points away from the positive charge towards the negative charge. So this is the electric field. Let's assume we start at an initial position here and we have a final position here. Okay, and we want to see we want to basically try to derive the equation for the capacitance. Remember, capacitance, we said the governing equation is that Q is equal C delta V. And we have seen in chapter 24 that delta V is minus the integral of E dotted ds. So this is C times minus the integral of E dotted with ds. Okay, and you notice here the electric field E and the vector ds are 180 degrees apart. So this is going to be equal C minus E cosine 180 degrees ds. Okay, cosine 180 is minus 1, so this is equal to C E ds from initial to the final position. Okay, so this is a charge Q. Now, what is the electric field in this case? So we can use a Gaussian surface. Let's assume we have a cylindrical Gaussian surface here, and we want to determine the electric field between the two plates. Remember, so the Gauss's law says the flux is E dotted with dA is equal to the charge enclosed divided by epsilon 0. Okay, so let's assume, for example, that in this case we have a charge per unit area sigma. The charge per unit area is sigma. So this is notice that electric field inside the conductor here, there is no electric field, so the electric field on this one is 0. Okay, so the electric field on this plate is 0. On this plate, the electric field is perpendicular, so the electric field is perpendicular to the area vector. So the flux here is 0. The only remaining flux is on this area, and so we can write this is equal to E times A is equal to the charge enclosed. In this case, the charge enclosed is sigma, the charge per unit area, times the area divided by epsilon 0. So we can see the area will cancel, and we get the electric field is equal sigma over epsilon 0. We have already done this before. So now let's replace this in this equation. So we can write Q is equal to C sigma over epsilon 0 ds. So sigma over epsilon 0 goes out of the integral, and so this will become C sigma epsilon 0, and the integral of ds from I initial position to the final position which is C sigma. This is the distance D. So let's assume this is the distance D. Okay, so C sigma D divided by epsilon 0. So let's replace sigma by its equation. It's the charge per unit area, so we can write Q is equal to C. Sigma is a charge per unit area times D divided by epsilon 0. You can see the charges will cancel and we obtain the capacitance. C is equal to epsilon 0 A divided by D. Okay, so this is the equation we wanted to prove. All right. So this is again the derivation. You can check it, and let's go to another case. Let's assume we have a cylindrical capacitor. So the cylindrical capacitor is made out of two concentric cylinders, one of inner radius A and one of radius B, and there is an insulating air or vacuum or an insulator in between them, so it's an empty space. Let's assume the length of the capacitor is L. In that case, the capacitor is given actually by 2 pi epsilon 0 times the length of the capacitor divided by log of B over A. Okay, so log of B over A, and let's try to verify this. Okay, we will do the same derivation as we did earlier. Okay, so let's assume this is the inner cylinder of radius A, so this is the inner cylinder. This is the outer cylinder of radius B. Okay, let's assume we have a positive charge Q on the outer surface and then minus Q on the inner surface. So the electric field points from the positive to the negative direction. And let's assume we start at the inner circle and we want to reach the outer circle. And we want to write the equation for capacitor. Q is C delta V. Okay, and we know the delta V is minus E dotted with ds. So this is C times minus E dotted with ds from initial to final position. Okay, again, notice the electric field is 180 degrees, makes an angle of 180 degrees with the displacement vector ds. So we can write this is equal to C the integral of E ds from initial to the final position. Okay, so let's try to determine what is the electric field between these two cylindrical surfaces. So let's make this as a Gaussian surface. So this is here, we have a Gaussian surface of radius r, small r, and let's write the flux is equal the integral of E dotted with dA, which is equal to the charge enclosed divided by epsilon 0. Okay, so again, for this cylinder, the only electric field that will contribute is the electric field on this belt. Okay, and in this case, the electric field and the area vector are parallel to each other. So we can write that in this case, E times the area of the cylinder, which is the circumference of the cylinder, 2 pi r times L, is equal to the charge enclosed. So let's assume this spherical Gaussian surface includes the whole capacitor. So this will be Q divided by epsilon 0. So we can see that we can get the electric field is Q divided 1 over 2 pi epsilon 0 divided by L times R. So let's replace this in this equation here, and we get Q is equal to C, the integral. Okay, so now we replace ds by dr, and we are going from A to B, 1 over 2 pi epsilon 0 Q divided by LR dr. So let's take everything outside of the integral except 1 over r. So this is going to be equal C over 2 pi epsilon 0 Q divided by L, the integral from A to B of 1 over r dr. Okay, the integral of 1 over r is log of r, so this is going to be C over 2 pi epsilon 0 L times Q log of B minus log of A, so that's log of B divided by A. And notice, so the Q's will cancel and I can get the capacitance C is just equal 2 pi epsilon 0 L divided by log of B over A. So this is the equation for capacitance, which is the same as this equation. Okay, so this is a cylindrical capacitor, and we derived the equation for a cylindrical capacitor. So this is the same derivation, you can go through it on your own. Okay, for a spherical capacitor we can do the same thing. Okay, so the equation, this is a spherical capacitor with an inner sphere of radius A, a conducting sphere, and an outer conducting sphere of radius B. And in this case, the capacitance is actually equal to 4 pi epsilon 0 A times B divided by B minus A. And we can write it, it's 1 over K, because K is 1 over 4 pi epsilon 0 AB divided by B minus A. All right. Okay, so let's derive this, and we will do the same method. Okay, so let's assume we have the outer spherical surface has a charge Q, the inner surface has a charge minus Q. So this is the electric field established between the positive and the negative terminal of the capacitor. Okay, and let's assume the initial position is on radius A, the outer is on radius B, and we want to determine the capacitance. So we write Q is equal C delta V, and we know that delta V is minus the integral of E dotted with ds. And since ds makes an angle of 180 degrees with the electric field, so this is the electric field here, and ds they make 180 degrees, this is equal to C, the integral of E ds from initial to the final position. So again, we need to determine the electric field inside of this capacitor. So let's use Gauss's law. So let's use, for example, this is as our spherical Gaussian surface of radius r. So we can write the flux is the E dotted with the A, okay, which is equal to the charge enclosed, divided by epsilon 0. Okay, all right. So here the electric field is constant over this spherical surface. So we can write that this is equal to E times 4 pi r squared. This is the area of the sphere, is equal to the charge enclosed. Okay, so the charge enclosed in this case is minus Q divided by epsilon 0. Okay. All right, so let's say the electric field is equal for 1 over 4 pi epsilon 0, 1 over 4 pi epsilon 0, and Q over r squared. So we have a minus sign, okay, in this case. All right, so let's plug this. Let's make sure that everything is correct, okay. So let's plug this into this equation, and we obtain Q is going to be equal to C, and the integral from initial to the final position, so it's from radius A to radius B, okay, and this is 1 over 4 pi epsilon 0 Q over R, r squared here, r squared, okay, so it's 4 pi r squared, so r squared dr, okay. So let's take the constant outside of the integral. This becomes equal to, we have a minus sign also, so C divided by 4 pi epsilon 0 times Q, and we have the integral of minus 1 over r squared dr, okay, from radius A to B. What is the integral of minus 1 over r squared? It's 1 over r, so this becomes equal to the charge Q is going to be C Q divided by 4 pi epsilon 0, and we have 1 over r, and this is evaluated between A and B, okay, so this is going to be equal C Q divided by 4 pi epsilon 0, okay, so we have 1 over B minus 1 over A, okay, it looks like somehow. Right, so this is going to be equal to CQ, yes, CQ divided by 4 pi epsilon 0. Okay, so we have A minus B divided by AB. Actually, somewhere we might have made an error of the minus. Okay, so let's use only the magnitude of the electric field. So if we use only the magnitude of the electric field, this will be positive, this will be positive, so we will have a minus, so we'll have a minus here, so this will become B minus A, B minus A. So if we eliminate the Q's from this equation, we get C is equal to 4 pi epsilon 0 times AB divided by B minus A, okay, which is this equation. All right, so we have proven the equation, or that the capacitance of a spherical capacitor is 4 pi epsilon 0 AB times AB divided by B minus A. Okay, so you can check, this is the derivation, okay, and okay, yes. All right, so what if we have an isolated sphere? An isolated sphere is equivalent to two spherical surfaces, except the outer surface, the radius goes to infinity, b goes to infinity. So if we take the limit of this when b goes to infinity, this will be, c is going to be equal to 4 pi epsilon 0 times a. So the limit of ab divided by b minus a when b goes to infinity is equal to ab. So it is, sorry, is equal to A. Okay, so the capacitance of just a spherical capacitor with only one surface is 4 pi epsilon 0A. All right, or the A, which is the radius of the sphere in this case. Okay.